Hi. Repetition is one of the pillars of education. So let's think about linearization again from a slightly different perspective. We do this by considering differentials. We will come to what a differential is exactly in a moment, but let's note first that we are aiming to consider two things with this definition. First of all, we want to define something that easily allows to change the point about which we linearize a function. Secondly, we want to consider a gadget that allows us to quickly approximate not a particular function value, but rather how much that value changes for a particular change in input value. To start with that second point, let's consider the following picture of the graph of a function, and suppose we already know the value of the function at the point x0, and would like to know the value of the function at the point x, which is equal to x0 plus some difference delta x. In particular, delta x equals x minus x0. Since we already know the value at the point x0, it is enough to know the difference delta y caused by the difference delta x, as you can see in this picture. As shown, delta y equals f of x minus f of x0. However, as is the guiding principle of this week's lessons, it may be hard to determine delta y exactly. Instead, let's consider the approximation we would obtain if we use the linearization at the point x0. Here you see that by using the linearization to approximate delta y, we would obtain the value dy shown in the picture. Indeed, since delta y equals f at x minus f at x0, we find for dy the value L at x minus L at x0, which equals the derivative of f at x0 times x minus x0. If we recall that x minus x0 is equal to delta x, we find that dy equals the derivative of f at x0 times delta x. So, to quickly approximate the change in a function value due to a change in the input, we simply consider the value of the derivative at the original point times the change in input value. How about our first consideration? Namely, that we want a gadget that allows to easily change the point about which we linearize. In fact, it already works out, if we simply allow the point x0 to vary in the obtained formula. Thus, we obtain the definition of a differential. Given a function f, the differential of f, denoted df, is given by the derivative of f at x times dx. Here, both x and dx may vary. In practice, x is given by the point at which we consider linearization, and dx is given by the change in input. In that case, the differential df approximates the change delta f that the function undergoes when we go from f at x0 to f at x0 plus delta x. As an example, let's consider the function f of x equals x cubed plus 2x squared. Then the derivative of f equals 3x squared plus 4x. And so, df equals 3x squared plus 4x times dx. In particular, if we want to approximate the difference between f of minus 1 and f of minus 0.8, we have delta x equal to 0.2, and so df equals minus 0.2. In this case, we may also compute the actual value of f at minus 0.8, exactly, to find that delta f equals 0.232. So that our approximation error is exactly 0.032. The differential is often used to approximate propagation of error. That is, we interpret delta f as the resulting error in the output value due to an error delta x in the input value. This appears in particular when there is some uncertainty in the actual value of the input parameter. In those cases, we refer to the differential df as the approximate error. The approximate relative error is given by dividing the approximate error by the value of the function at the point of approximation. So df divided by f of x is called the relative approximate error. It is often the relative error that matters in applications. Please be warned that although it has the same name, this notion of error is different from approximation error we have been considering. In particular, here we are approximating an error. For example, suppose a company constructs steel cylindrical beams of length 8 meters and the diameter of each beam is 0.6 meters. Due to some uncertainty in manufacturing, we may expect a possible error in the diameter of at most 0.01 meters. Can we quickly approximate the resulting error in the volume of the beams so that we may take this into account when deciding how much resources we need? Using differentials, this becomes very easy. The volume of a cylinder is given by the length times pi times the radius squared. So, since the beams are 8 meters long, we find that the volume V as a function of the diameter x equals 8 times pi times x over 2 squared. So, the differential dV equals 4 pi x times dx. Thus, since the expected error in the diameter is 0.01 meters and the diameter is 0.6 meters, we find that the expected error in the volume is 4 pi times 0.6 times 0.01, which means 0.0754 cubic meters. The relative error in the diameter is dx over x. In this case, we have 0.01 over 0.6, which equals 0.016, or 1.6%. The resulting relative error in the volume is approximately dV over V. In this case, this is 0.0754 over 8 pi times 0.3 squared, which equals 0.03333, or 3.3%. In other words, the expected error of 1.6% in the diameter means we should account for an approximate increase of 3.3% for the necessary resources. Please make sure to test what you learned by considering the exercises following this lesson.